Hello everyone, this is Samiul Islam, one of the academic members of Center of Circle. Today we are going to discuss two-body problem and Kepler's laws. I have divided the topic into three chapters. Today we will be looking at chapter 1, which is reducing the two-body problem into one-body problem and finding the equation of motion. So, I have divided today's chapter into three subtopics, which are vectors and coordinates in a two-body system, and Lagrangian approach, and central force equation. So let's do a quick overview on the topics of today's chapter. At first, vectors and coordinates in a two-body system. In this topic, we will build up some relation between the coordinate system and the position vector of the objects in a two-body system. But at first, we will set up our coordinate system and then we will build up these relations. In the second topic, which is Lagrangian approach, we will write some energy equation and we will calculate the Lagrangian and build up some relations with the energy and angular momentum and other stuffs. In the third and the last topic of today's lecture, which is central force equation, we will develop a force equation for our two-body system. But we will not solve the equation in today's chapter. We will be solving this equation in the next chapter, in the next video. So, before starting, let's make sure that we know what is exactly a two-body problem. In classical mechanics, a two-body problem is to predict the motion of two massive objects which are abstractly viewed as point particles. It is a definition which is taken from Wikipedia. Let's cut the definition into pieces. So here it is said that a two-body problem is to predict the motion of two massive objects which are abstractly viewed as point particles. So the first thing is, in a two-body problem, there will be two massive objects such as planets or stars. But we will consider them as point particles. And our job is predicting the motion of the point particles in order to solving the two-body problem. So at first, here you can see there are two objects in the space with mass m1 and mass m2. So the object with mass m1 is located at a distance of r1 from our coordinate system, which is a Cartesian coordinate system, and mass m2 is located at a distance of r2 from our coordinate system, from our origin of the coordinate system. So here r1 is the position vector of m1 particle and r2 is the position vector of m2 particle. There is another position vector which is smaller. It is the distance between particle m1 and m2. So with some basic vector geometry, we can figure out what is small r. Here our small r is the difference between the position vector of m2 and the position vector of m1, i.e. the small r is r2 minus r1, and the capital M is the total mass of the system. As there are two masses in the system, or two particles in the system, one has mass of m1 and another has mass of m2, the total mass of the system will be the sum of the masses of the particles, which is m1 plus m2, and we denote it by capital M. Here we can see another equation, which is capital R, which is equals to m1 r1 plus m2 r2 divided by capital M. Here capital R is the position vector of center of mass, which is not drawn in this figure, but we will be talking about this. Capital R is the position vector of the center of mass of the system, and it is m1 r1 plus m2 r2 divided by capital M. So these were some basic calculations from the coordinate system and the vectorial representation of our two-body problem. So here, as we can see, small r equals to r2 minus r1 and capital R equals to m1 r1 plus m2 r2 divided by capital M. If we substitute r2 from our first equation, which is r2 equals to r plus r1, then we find capital R equals to m1 r1 plus m2 into r plus r1 divided by capital M. If we solve the equation and do some basic algebra, we can see r1 equals to capital R minus m2 by capital M into small r, and r2 equals to capital R plus m1 by capital M into small r. These are nothing but the relation between the position vector of the particles and the center of mass of the system. These are some important relations. As we can see, we will be using this relation instead of this relation in the future equations. So note down this in a notebook and just try to remember these two equations. So here we can see the first equation of physics in our today's lecture, which is a kinetic energy equation. As written, K equals to half m1 r1 dot square plus half m2 r dot 2 square. So the kinetic energy of a system is the sum of all kinetic energy of all particles in the system. In a two-body problem, well, let's consider space with lots of planets. So what we can see, there are a lot of planets, Earth, Moon. Sorry, Moon is not a planet, but yeah, you can think it as an object, a massive object. So Earth, Moon, Sun, Saturn, Jupiter. So lots and lots of objects, massive objects in our solar system. But we are interested about, let's assume, Sun and Earth system. So how many objects are there in our system? Well, there are two objects, and because of the number of objects is 2, so our problem is a two-body problem, which you can say Earth-Sun system. In this problem, we will neglect all the forces due to other objects such as Saturn, Moon, and Jupiter, etc. And we will ignore their kinetic energy, their masses, and their forces in our system. So basically, a two-body problem is an isolated system of two massive objects. So the kinetic energy of the system will be the total kinetic energy of the two particles, which is half m1 r1 dot square plus half m2 r2 dot square. Here r1 dot is the time derivative of the position vector of m1 particle, and r2 dot is the time derivative of the position vector of m2 particle. Previously, we developed some relation between R1 and the center of mass, the position vector of center of mass R, capital R, and R2 with the position vector of center of mass, capital R. Here are the relations. And here is the kinetic energy equation. So what we can do, we can substitute R1 from here to here and take its time derivative to make half m1 r1 dot square, and we can substitute r2 from here to here and take its time derivative to make half m2 r2 dot square. We will calculate it in this page. So in this picture, in this page, we will derive the equation which is written here, this kinetic energy equation, from this kinetic energy equation by substituting this R1 and R2 from here to here. So first of all, I cannot draw too good, so I am trying my best to draw this. Where's my pen? Yes, there's my pen. So our equation was something like half m1 half m1 and r1 square. So r1 dot square, here r1 is capital R minus m2 by capital M into small r, so r1 dot will be capital R dot minus m2 by m small r dot, as m2 by m is constant. So let's move again my pen. So where we can write, instead of r1 dot, we can write capital R dot minus m2 by capital M times small r dot. Well, this is not this yeah, now it's right. No, okay, so it will be m2 divided by capital M into small r dot whole square plus half m2 times r2 half m2 times, well, I can move my equation. I can move this part. Well, give me a little bit of time to move this part there and this part here and this part here, so as I can write, so that I can write my equation in one line here and this one. It's a lot of work to do. Well, yep, we can do this. Yeah, here equation, we place the equation in right places so that I can write the whole equation in one line. So our our small r2 dot was r capital R dot plus m1 by capital M times small r dot whole square is our parenthesis and here is square. Well, that was our kinetic energy equation. So if we calculate it with some basic algebra, then we can find there will be messier to write this equation in the computer screen. So I'm skipping the part of writing this whole calculation here, but I will show you what we exactly find from the equation if we solve this. Here I'm showing you it is half m1 capital R dot square plus half m2 times capital R. Sorry, my R is little bigger. I can remove it and draw again. That's my pen. Ah. So it is m2 capital R dot square plus, here's our key term. It is our key term, so please try to concentrate in this term, which is m1 m2 divided by m1 m2 divided by m1 plus m2 m1 plus m2 into r dot square. So if we solve this equation, this square equation, and do some basic algebra, we come over this equation, half m1 capital R dot square plus half m2 capital R dot square plus half m1 m2 divided by m1 plus m2 into small r dot square, where you can see we can make it half m1 plus m2 into capital R dot square, which will be half capital M, as capital M is m1 plus m2, capital M R dot square plus this term. Here our this term. This is called the kinetic energy about the center of mass, and this term is called the kinetic energy of center of mass. So here we can see half m1 m2 divided by m1 plus m2. This term has same dimension as mass, so we can consider it as another mass. We will be calling it reduced mass, and it will be denoted with the letter mu. mu r dot square. So now our final kinetic energy equation is this, which is half capital M r dot square plus half mu r dot square. So as you can see in our previous slide, here I have written the reduced mass mu equals to m1 m2 divided by m1 plus m2. Where did this come from? This comes from our algebraic calculation of the kinetic energy equation of this equation after substituting r1 dot and r2 dot with the value of r1 and r2, which we developed in our previous calculations. So after doing some basic algebra, we came into this equation, half m1 capital R dot square plus half m2 capital R2 R dot square plus this term. This is called the center of mass. This is called the kinetic energy about the center of mass, and this is called the kinetic energy of the center of mass. So these were the proof of this equation from this equation. Now our at first this equation had 6 degrees of freedom, as r1 dot has 3 coordinates, x1 dot, x2 dot, and x1 dot, y1 dot, and z1 dot, and r2 dot had 3 coordinates, x2 dot, y2 dot, and z2 dot. So total number of degrees of freedom was 6. It was a nightmare to solve an equation with 6 degrees of freedom. That's why we did some basic algebra and we did some substitution of r1 and r2 with our previous relations with the center of mass equation. And then we came into this equation, which is half capital M capital R dot square plus half mu small r dot square. It has a degree of freedom of 3. Why? Because small r has 3 coordinates, x, y, and z. So now you can ask a question, what about this term? Well, this term is called the kinetic energy of the center of mass, but this term will be vanished somehow later. We will see this in the later slides. So here our first topic of today's lecture ends, which was the vector and coordinates of a two-body problem. We will do a recap on the topic right now. So at first we placed 2 objects in space, and then we developed the vectorial relation of the objects with the coordinate system, which are written here. Then substituting the vector, the displacement vector of between the 2 particles in the equation of the center of mass, we came into this relation, the position vector of the first particle with the center of mass position vector, and the position vector of the second particle with the center of mass position vector. These are the 2 important relations which will be substituted in our next equation, which is our kinetic energy equation. So in this kinetic energy equation, it was a 6 degree of freedom equation. We substituted r1 dot and r2 dot that they were previously found in this relation. After substituting and doing some basic algebra, we came into this equation, which has a degree of freedom of 3. So now we will be moving in our second topic of today's lecture, which is Lagrangian approach. So at first I will do some basic introduction with Lagrangian. So as you can see, here is written an operator which is called a Lagrangian is equals to T minus U, where T is our kinetic energy and U is our potential energy of the system. So what is a Lagrangian? In simple words, well, at first I want to clarify something. We will not look into deeper of Lagrangian, so I'm not mentioning the exact physical meaning of Lagrangian here, but I will look into just mathematical stuffs here. So yeah, uh, in order to mathematics, Lagrangian is the difference between the kinetic energy and the potential energy of the system. So here our kinetic energy was half capital M capital R dot square plus half mu small r dot square minus that was our kinetic energy, and our potential energy is U of R. We don't know what is our potential energy, so it is some unknown function. We want to write this, that it is some unknown function, unknown function. So as potential energy is a function of uh, position, so we write this as a function of R, but it is unknown. We don't know yet what is our potential energy or what is our potential function. So yeah, it's unknown. Well, here we can see an equation which is a differential equation. It is called Euler-Lagrange equation or Euler-Lagrange equation, which is nothing but partial derivative of Lagrangian with some variable q is equals to time derivative of partial derivative of Lagrangian with the time derivative of that variable q. So we can find this equation from variational calculus, which is not our relevant topic of today's lecture. We can see something here the variable q, we took it the center of mass r, and q dot is r dot. So if we take the time derivative of this Lagrangian with respect to r, then it will give us 0, as there is no function, which is a function of capital R. So the equation is independent of capital R. Thus the derivative respect to capital R will be 0. On the other hand, that means this part is 0. What about this part? At first, the partial derivative of Lagrangian with respect to r dot is m r dot, as this term is independent, this term is independent of r dot, and this term there is r dot. So if we take derivative of this respect to r dot, then it comes m r dot. So the time derivative of m r dot will be 0, as the left hand side is 0. That means m r dot is constant, and as capital M is the total mass of the system and it is constant, so r dot is constant. Here we wrote that r dot is constant. As r dot is constant and we don't know what is the value of the constant, we can choose, we have the freedom to choose it 0. So we chose r dot equals to 0. It is a constant and it is 0. Thus r equals to 0, and r equals to 0, that means our origin, it is at the center of mass, or in other words, our center of mass is located at our origin. Well, in the previous slides we developed some relation with the position vector r1 and the center of mass position vector capital R, which was r1 equals to r minus m2 by m into small r, and r2 equals to r plus m2 by m into small r. So right now we saw that r equals to 0. That means r1 equals to minus m2 by m into small r, and r2 equals to m1 by m into small r. So it's now easier for us to move forward and solve other equations, as there is no additional terms here. It is now a simpler single term equation, singular term equation. So yep. So here we will be calculating the necessary equations. So now we will look into our kinetic energy equation again, which was half uh, capital M capital R dot square plus half mu dot, sorry, not mu dot, it's mu times small r dot square. As you can see, r dot was constant and we chose our constant to be 0. That means this term cancels out. Oops. This term cancels out, which becomes 0. Yes, this is nothing but 0. So now our kinetic energy becomes a simple equation, which is T equals to half mu r dot square. Now as you can see, it is a equation of 3 degrees of freedoms. So what we just did, we reduced a equation with 6 degrees of freedoms to a equation of 3 degrees of freedom. So that is the main key concept of these words. So let's recap. At first, we saw that our Lagrangian was this, and from Euler-Lagrange equation, we chose a variable q to be r and q dot is r dot. And we took the Euler-Lagrange equation, we solved it, and we found that r dot must be constant. As why r dot will be constant? So we can look at here again. R dot equals to constant because of d by ddt of capital M times r dot equals to 0. This equation is the key concept. That's why r dot is constant. As capital M is constant, so r dot must be constant to make its derivative, its time derivative, 0. So as r dot is constant, we can choose it to be 0, as we have the freedom to choose any constant, as we don't know what the constant is. So as r dot is 0, then r is 0. R is 0, that means our center of mass is located at the origin. And then we developed some vector equations in our first topic of the lecture. So we substituted the value of r in those equations, and we come into some smaller and simpler equation of our position vector r1, position vector r2. Then we substituted the value of capital R dot into our kinetic energy equation, which we developed here in this equation. In this equation, we just substituted r dot, which is equals to 0, and then we find our kinetic energy is equals to half mu small r dot square. Here you can see now it is more like a one body problem than a two body problem, as there is just one kinetic energy equation with one mass and one position vector. Though it is not a single mass, it is reduced mass. A reduced mass and a single mass are different um, in order to their physical meaning. Well, then we move into our next slide, which is the angular momentum. Why angular momentum is necessary? Because by the concept of angular momentum, so our question was why angular momentum is necessary. So as we can see, angular momentum is a cross product. So a cross product is gives a result which is perpendicular to our working plane. So our angular momentum is r cross p, where r vector is nothing but uh, so r cross p, r vector cross p vector, so which is r1 cross m1 times r1 dot plus r2 cross m2 times r2 dot. So I will skip the calculations as it will get messier and it will take a lot of times. But what you can see, if you substitute R1 and R1 dot with the values we found here, where R1 was equals to minus M2 by capital M into small r, and R2 equals to small small m1 divided by capital M into r. If you substitute R1 and R2 from here to here, then we find L, which is our angular momentum vector, is equals to mu times small r cross small r dot, where mu is our reduced mass. It is a constant. Why it is a constant? Because our reduced mass term is a constant which we defined in our previous slides, and position vector r is constant, so r1 r cross r dot will be constant. Angular momentum is a constant quantity, and here our angular momentum is written in terms of reduced mass. So what I was saying previously, that angular momentum is necessary because it reduces our degree of freedoms of our equation. Previously, we established a equation, kinetic energy equation, which had 3 degrees of freedoms. But right now, with the help of angular momentum, we come into an equation which has a degree of freedom of 2. Why? Because L vector equals to nothing but 0, 0, LZ, as our objects are in xy plane, sorry, my bad. As our objects was in xy plane, so the angular momentum component will be perpendicular to the plane, which is z component. So right now we have 2 degrees of freedom, which is x and y. These two are now the degrees of freedom. Now we can solve this equation with 2 degrees of freedom, as r dot had 3 degrees of freedoms, which were x, y, and z, x, y, and z, where z component vanishes as the uh, as the motion in the motion of our system is in xy plane. So the z component of r vector, the position vector of r, is vanishes from the concept of planar motion. So the equation becomes simpler, and it has now 2 degrees of freedoms. So here our second topic of today's lecture ends. So let's do a quick recap of the second topic, what we learned and what we developed in this chapter, in this topic of this chapter. So at first we looked at the Lagrangian approach, and we learned what is Lagrangian, and we figured out what is our Lagrangian for our system, which was half capital M capital R dot square plus half mu times small r dot square. So it is our Lagrangian, it is our kinetic energy. So our Lagrangian will be kinetic energy minus potential energy, but we don't know what is our potential energy function. So here our potential energy function is unknown. So we denoted it with some function of r, u of r, and then we solved our Euler-Lagrange equation, where we took the variable q as the center of mass position vector r and q dot as r dot. After solving the Euler-Lagrange equation, we found that r dot equals to constant and constant, and we chose the constant as 0, and thus the position vector of center of mass becomes 0. That means the center of mass is at our origin, and we substituted the value of capital R in our previous vector relations with r1 and r2 with center of mass, and we found these two equations. Then we substituted the value of r dot in our kinetic energy equation, which we found in the first topic, which was half capital M capital R dot square plus half mu small r dot square. Here capital R dot becomes 0, and our kinetic energy equation becomes half mu small r dot square, which had 3 degrees of freedom. But after solving the equation of angular momentum, we saw that the existing angular momentum component is at z direction. So our motion will be at xy plane. Thus, the degrees of freedom reduces from 3 to 2. That's how our second topic of today's lecture ends. Now we will look into the third topic of today's lecture. Our goal was reducing the two-body problem into an one-body problem. Thus, we first reduced the degrees of freedoms of the equation. It was a 6 degree of freedom equation. Then we made it 3 degrees of freedom of equation by substituting the vectorial relations of position vector and center of mass position vector. Then from 3 degrees of freedom of equation, we made it 2 degrees of freedom of equation by solving the angular momentum equation and finding its component in the z direction. So here comes our last topic of today's lecture, which is central force equation. So here we can see we transformed our coordinate system from Cartesian to polar. So here is a polar coordinate system, which is written in terms of Cartesian coordinate system. So here you can see, here is the interesting part of today's lecture and the key part of today's lecture. Here you can see one blue dot, which is denoted by mu, and the position vector of this blue dot from the origin is small r, and this makes an angle of theta with horizontal axis or x-axis of our Cartesian coordinate. So what is mu and what is r? As you can see in this part that our kinetic energy equation was half mu small r dot square. There is a single equation. That means we can treat it as a kinetic energy of a particle. That means it can be treated the kinetic energy of one single particle. So that's what we drew here, that a single particle with mass mu is located at a distance of r from the origin, and it makes an angle of theta with the horizontal axis x-axis. So here we can write our position vector r vector equals to r times r hat. And as you know, I can assume that you all know how to find the coordinates of how to transform the coordinates from Cartesian to polar and polar to Cartesian. So as we can see, our velocity vector in the polar coordinate will be r dot r hat plus r theta dot theta hat. It is nothing but the ddt of r hat. Well, if we take time derivative of this equation again, then we find our equation of acceleration, which is written here: a equals to r double dot minus r theta dot square r hat plus 2r dot theta dot plus r double dot times theta hat. Here, this term is called Coriolis effect or Coriolis acceleration, and this term is called the centripetal acceleration, and this whole term is called radial acceleration, and this whole term is called tangential acceleration. So we are interested about the radial component of our acceleration vector. The radial component of our acceleration vector. So in the next slides, we will be working with this part of the equation, which is r double dot minus r theta dot square. So we are moving into our next slide. Oh well, there's a task. There's a task for you to prove that a theta is nothing but the tangential component of our acceleration vector. You have to prove that a theta equals to L dot divided by mu times r, where L dot is the time derivative of our angular momentum, and mu is reduced mass, and r is nothing but the position vector of mu from our origin in our polar Cartesian coordinate. So here's our two key equations. As you can see, these are two differential equations, but we will not solve them here, but we will talk something about these equations. As you can see, we have our velocity vector here, which is r dot r hat plus r theta dot theta hat, and we knew that our kinetic energy is half mu. Oh well, I did some mistakes here. Here small m's will be mu. It is not small m, it will be mu. So let's correct our mistake. So as you can see now, it is corrected. So r dot equals to something something and theta dot equals to something something. So what does that mean? And where it has come from? So here you have to think about something, that L, or our angular momentum, was mu times r cross r dot, which can be written as r square theta dot. It is all up to you to calculate the things and check it out. So from that relation, we can find theta dot equals to L by mu times r square, and r dot, where does this come from? This comes from the relation of this. Our kinetic energy is half mu v square, and v is what? V is that. So square of this times half mu comes from this equation. It comes our kinetic energy equation, which is half mu v square, and whereas v is this r dot r hat plus r theta dot theta hat. So if we solve r dot from that equation, then we find it is root over 2 by mu times e minus u of r minus L square by 2 mu r square. Here E is the total energy of our system, which is kinetic energy plus potential energy. As we mentioned earlier, that our potential energy is some function of r which is unknown. So here, because of this, we denoted the potential function as u of r. We don't know yet what is the function of potential here. And minus L square divided by 2 mu r square, it is nothing but these terms, this term r theta dot, as you can see, theta dot is L by mu r square. If we square it, then we find L square by mu square, then r to the power 4, and then if we multiply this with r square, mu r square, then we find r square by 2 mu r square, and this terms. Well, here u of r minus L square by 2 mu r square, this term is called the effective potential. This is the effective potential which we will be looking at in our next lecture, chapter 2. So the main reason of writing this equation was, here are two differential equations, r dot and theta dot. R dot is a function of t. That means r dot is the time derivative of position vector r. That means the position vector r is a function of t. If we write this, we can write that as where's our slide? Sorry. Yeah, we can write this as here's my pen. Yeah. So we can write this as r dot exists. R dot exists. That means r is a function of t. R is a function of t. And theta dot exists. That means it is a function of theta is a function of t. So we found r as a function of t and theta as a function of t. Now we can determine we can write some equation r as a function of theta, and then we can solve this and we can find the equation of motion for this system. But here is a key concept. Here is a problem here. We don't know what is this function. This is an unknown potential. So we cannot substitute it with theta. We cannot write it in terms of theta, as we don't know what is the potential function of our system. So here we've developed two differential equations from our previous calculations, which were the total energy equation and the polar coordinate velocity. From these two equations we find r dot, and from our angular momentum equation we find theta dot. But we cannot direct solve these equations, as we have an unknown potential function in our equation. So what can we do? We can write force equation. Whereas energy equation is not solvable, then we can write a direct force equation. As we know, force is ma, F equals to ma, where in our context our m is mu, as we reduced our two body problem into a one body problem with mass mu, and its acceleration is nothing but the radial component of the acceleration vector, which is a of r equals to f of r. It is a position dependent force. As you can understand, it is a position dependent force. So mu a of r equals to f of r, where a of r is r double dot minus r theta dot square, and theta dot is as we can see, theta dot is L by mu r square. If we substitute it here, then we find L square by mu square r square, mu square r cube. r to the power 4. And here's this r cancels one r, that it becomes r cube. So finally we found r double dot minus l square by mu square r cube equals to f of r by mu. This equation is called central force equation. It is a second order differential equation. If we solve this, then we found our position vector r, and we can found then we found our position vector. Then we will find our position vector. What is our position vector r? So by solving this second order differential equation, we can determine the orbit, the path of our two body problem, in which path the object follows each other. We can determine the orbit and the path of motion by solving this second order differential equation, which we will be solving at our second lecture, at our second chapter. So here's our last topic of today ends. So we will now do a quick recap what we developed today, what we learned today in today's lecture. At first, in the first topic of today, vectors and coordinates in a two-body system, we just placed two objects of mass m1 and m2 in space. The distance of m1 and m2 was respectively from our origin was r1 and r2. These were the position vectors of m1 and m2. The displacement vector between m1 and m2 was r, small r. From vector geometry, we found that r equals to r2 minus r1. And the total mass of the system was m1 plus m2, and this was the center of mass equation, or the position vector of center of mass. And then we substituted r2 and r1 from our first equation to the position vector of center of mass equation, and then after doing some basic algebra, we found a relation between the position vector of m1, which is r1, and the center of mass of the system, and the position vector of m2, which is r2, and the center of mass of the system. These are the relations. These are some important relations because we substituted these relations into the next kinetic energy equation, which was half m1 r1 dot square plus half m2 r2 dot square, and we substituted the value of r1 and r2 here and took the time derivative. Then we found something which was half capital M capital R dot square plus half mu small r dot square, where mu was this term, which is called the reduced mass. Here ends our first topic. What we did was nothing but reducing a 6 degree of freedom equation into a 3 degree of freedom equation, and this was our first step to reduce the two body problem into a one body problem. And then the Lagrangian approach, we introduced our Lagrangian, which was kinetic energy minus some unknown potential, and then we used Euler-Lagrange equation, where we declared the variable as center of the position vector of center of mass and the time derivative of position vector of center of mass. Then we solved Euler-Lagrange equation, and we came into a decision that our time derivative of position vector of center of mass is a constant, and because of having the freedom of choosing a constant, we chose our constant as 0. That means our center of mass was at origin. And then from the first vector equations from first topic of today's lecture, we substituted the value of r in this vector equations, and we found the position vector of r1 and position vector r2. Well, then we substituted the value of r dot in our 3 degree of freedom kinetic energy equation, and then we found one singular term, which is half mu r dot square. It is now a singular term, and it had 2 degrees of freedom, as we can see from our angular momentum equation, which has a component in z direction. That means our motion is in xy plane. That means this had a 2 degrees of freedom, which is x coordinate and y coordinate. Lastly, there was a task for lastly we came into a equation came into the topic of central force equation, which we transformed our Cartesian coordinate to a polar coordinate, and then there is a point, there is a blue dot, which we reduced our two bodies into a singular body, and we declared its mass as mu, which is our reduced mass, and the position vector of mu from origin is r, and it makes an angle of theta with the horizontal x-axis. Then we did nothing but wrote the equation of velocity and acceleration in polar coordinate, which is your task to prove them. And then there is another task for you guys to prove that a theta equals to L dot by mu r. After substituting the velocity of polar coordinate in our kinetic energy equation, which is half mu v square, we find in our total energy, which is half mu v square plus our unknown potential u of r, we do some basic algebra and we solve for r dot, which is r dot equals to this and theta dot equals to this. These are two differential equation. R dot exists, that means r is a function of t. Theta dot exists, that means theta is a function of t. That means we can find something r as a function of theta. But there is a problem, which is u is an unknown potential. We don't know what is u. That means we cannot solve r dot directly, and we cannot substitute theta, and we cannot write r in terms of theta because of this unknown potential. So what can we do? We will not use the energy equation. We just use the energy equation to reduce the degrees of freedom of the equation. But we will use a force equation to find the differential equation, where there is our force equation ma, where m is mu and a is the radial component of our acceleration vector. Then we did some basic algebra, and then we found this differential equation, which is the central force equation. From this second differential equation, this second order differential equation, we will find the path and the orbit of the central motion, and we will determine the orbit of the two body problem, and we can predict the motion of the two body problem by solving this second order differential equation. We will solve this equation in our next lecture. This is a second order ordinary differential equation. We will see how can we solve this with substitution method, and how can we determine our orbit of the two body problem. So that's it. That was for today. Yep. You guys are given a task, so try to solve this. So yeah, it's for today. Signing out.